Okay, my dear students, we are going to revise this fifth unit topic, IR spectroscopy and its applications. Okay, we have already finished this class, so we are going to revise this. So we already know few terms. We'll revise again. Okay. Spectroscopy is a technique used to determine the structure of a compound by the study of the interaction between matter and electromagnetic radiation. This term we already know. Okay, you can you can see here electromagnetic radiation in UV visible spectroscopy. What happens? There is excitation of electrons, and then UV visible, we get UV visible spectrum. Okay, in IR radiations, in spectroscopy, the IR radiations, they interact with the molecules, and there is vibrational changes, vibrational and as well as rotational changes, and we get the IR spectrum. Okay, and this is an NMR. Radio frequency interacts with the molecules. There is spin rotational changes, and we get NMR spectrum. Okay, we already know this electromagnetic spectrum, and in electromagnetic spectrum we are discussing about IR spectra, so we should know IR region. The IR region, IR region is still divided into three categories: near IR, mid IR, and phi IR. So the total region is 50 per centimeter to 12,500 per centimeter. The near IR region is 12,500 to 4,000 to 12,500 per centimeter. Mid infrared region 667 to 4,000 per centimeter, and far IR region is 50 centimeter to 667 per centimeter. Okay, so this is our IR region. We should remember, as far as our examination is concerned, they may ask write IR region spectrum or IR region. Okay, now we come next important topic, the principle of IR spectroscopy. We know that molecules, they are made up of atoms, and they are linked with each other through covalent bonds, through bonds. Okay, the movement of atoms and the chemical bonds, like it is like spring and ball. It is these bonds, they behave like springs, and the atoms, they behave like balls. Okay, so there is a ball and a spring like relationship in the molecules. Okay, and these bonds, they can be stretched, they can be compressed, and at equilibrium they can be rotated also, like we discussed in conformation and analysis. Rotations through one bond, it is possible. Okay, so this can happen in a molecule. These characteristic vibrations are called natural vibrations. They keep on vibrating, they keep on changing, they keep on stretching and compressing kind of things. They keep on happening in a molecule. Okay, at room temperature. So they have their own natural vibrations. The energy of the molecular vibration is quantized. The energy of molecular vibration is quantized. Okay, now, so what happens, we can use annotations. See, when the energy in the form of IR, electromagnetic radiation, is applied, or it is made incident on any sample containing molecules, atoms, or ions. Okay, when the energy in the form of IR is applied, and if the applied IR frequency matches with the natural frequency of vibration of the molecule, the absorption of IR takes place and a peak is observed. So it is the absorption of IR takes place when these two matches at resonance, they come at resonance. Okay, Then there is absorption of IR radiation, and we have one peak is observed in the spectrometer. Molecules are excited to the higher energy state from the ground state when they absorb IR radiation. When a compound is exposed to IR radiation, when a compound is exposed to IR radiation, it selectively absorbs the radiations resulting in vibration of the molecules of the compound. So it starts vibrating, okay, giving rise to closely packed absorption bands called IR absorption spectrum. We get IR absorption spectrum, okay. The bands correspond to the characteristic functional groups and the bonds present in a chemical substance. So these bands, they correspond to characteristic functional groups and the bonds present in a molecule, okay. Thus an IR spectrum of a compound is considered as the fingerprint for its chemical identification. It is like a fingerprint for the chemical identification of a given or unknown compound, okay. Now we can see here, when a molecule absorbs electromagnetic radiation in IR region, what happens? From ground state, it gets excited to the excited state. We have ground state and excited state, and there we have vibrational transitions from ground state to excited state, okay. This is electronic transition which happens in UV visible spectrum, but we are talking about IR spectroscopy. So there is the vibrational state changes, so vibrational transitions, okay, and as well as these are you can see here, these are vibrational changes. These are vibrational changes, and in between them, we have rotational levels, changes in rotational levels, rotational energy, rotational states, okay. So vibrational as well as rotational states changes, okay. We can see here, see, ground state and excited state, electronic excited state and electronic ground state. In the same, when the molecule absorbs IR radiation, we have vibrational levels. This V naught, 1, 2, 3, for excited, and the excited one also, okay. Same we have. And in between we have rotational levels. These rotational levels we have, okay. So vibrational states as well as rotational states, they change when the molecule absorbs IR radiation, okay. Here we can see. So when organic compounds, they absorb electromagnetic energy in the IR regions, IR does not have sufficient energy to cause excitation of electrons as in UV visible. It does not have that much energy. However, it causes atoms and group of atoms of organic compounds to vibrate faster. The molecules, they start vibrating very fast. They start vibrating very fast. The covalent bond which connect them vibrate through the covalent bond, okay, vibrate through the covalent bond, okay. We can see here ultraviolet IR region, it gets vibrating, okay. Molecule vibrates and rotates, it vibrates and rotates in when it absorbs electromagnetic radiation in the IR region. Here in ultraviolet region, this electron from ground state goes to the excited state, but here it does not have that much sufficient energy. So what it does, it starts vibrating and rotating. So a molecule in its ground state possesses three energy levels. It possesses three energy levels. We know that: electronic, vibrational, and rotational energy levels. We have discussed. Absorption in the IR regions is due to the changes in the vibrational and rotational levels. Vibrational and rotational levels. When an electron absorbs less energy, when an electron absorbs less energy, you can see here, when an electron absorbs less energy, rotational transitions take place when it absorbs very less energy. The spectrum observed is called rotational spectrum. In that case, we get rotational spectrum observed in the far IR region. Far IR region is 25 to 400 micron. Far IR region. Okay. But when the electrons absorb still higher energy, vibrational transitions take place, which is accompanied with rotational transitions. In that case, there will be vibrational as well as rotational transitions. Vibrational as well as rotational transitions. The spectrum observed is called vibrational rotational spectrum obtained in near IR region, 2.5 to 25 micron region. This near IR region. Okay. Electronic transitions take place at higher energies. In electronic transitions means UV in UV visible spectrum, when they absorb in UV visible spectrum, in UV visible region. Okay. In that case, there will be electronic transitions. But if they absorb less energy in IR region, there will be vibrational rotational spectrum. The spectrum observed is vibrational rotational spectrum, and the transitions are vibrational rotational transitions in that case. So the criteria for a compound to absorb IR radiation. So what is the criteria for a compound to absorb IR radiation? When the compound will absorb IR radiation? So the first criteria is there must be a change in dipole moment. There must be change in dipole moment. It must not be zero. There should be a change. It must not be zero. Okay. There should be a change in dipole moment. A molecule can only absorb IR radiation when its absorption causes a change in its electric dipole. Electric dipole. A polar bond is usually IR active. A polar bond, like we have carbon, double bond, oxygen, double bond, oxygen. It is polar. Okay. So it will be IR active. A polar bond is usually IR active. A non-polar bond in a symmetrical molecule will absorb weakly or not at all. It will not show, it will be IR inactive. Mostly it will be IR inactive. Okay. Now we come to molecular vibrations. Molecular vibrations. There are two types of molecular vibrations: fundamental vibrations and non-fundamental vibrations. We have two types of vibrations: fundamental vibrations and non-fundamental vibrations. So these fundamental vibrations again categorized in two groups, classified in two groups: stretching vibrations and bending vibrations. Stretching vibrations and bending vibrations. Again, in stretching vibrations, we have symmetric and asymmetric vibration. In bending vibration, we have in-plane bending and out-of-plane bending. Again, in in-plane bending, we have scissoring and rocking, and out-of-plane bending, we have wagging and twisting. Okay, we'll discuss all these things in detail. And on the other hand, non-fundamental vibrations are overtones, combination tones, and Fermi resonance, which is not there in our syllabus, and we will not discuss about these things. Okay. No. So as we have discussed, molecular vibrations, there are two types of molecular vibrations: stretching vibrations and bending vibrations. Stretching and bending vibrations. Again, they are categorized. Again, further they are divided. Stretching vibrations, we have, what are stretching vibrations? Vibration or oscillation along the line of the bond. Vibration or oscillation along the line of the bond. There will be change in bond length. There will be change in bond length. It occurs at higher frequency. It occurs at higher frequency. 1250 per centimeter to 4000 per centimeter. These are of two types. The stretching vibrations are of two types: symmetrical stretching vibration. Okay, let's see here. Symmetrical stretching and asymmetrical stretching. Symmetrical and asymmetrical stretching we'll discuss. Symmetrical and asymmetrical stretching. So this is one example of carbon dioxide molecule. Symmetrical stretching. These are the polarities which I have shown here. Oxygen partial negative. Both oxygen atoms, they have partial negative charge. The carbon will bear partial positive charge. So this is stretching, symmetric stretching, symmetric. So same time they are going out and coming back. Okay, bond length decreases or increases. You can see bond length decreases or increases. In bending, in-plane bending, okay, this is asymmetric stretch. See, one bond decreases, the other increases. One decreases, other increases, or the first increases, the second decreases. Okay, so this is asymmetric stretch. This is asymmetric stretch. Okay, you can see here. Symmetrical stretching. The first one, symmetrical stretching. Okay, both bonds increase or decrease in length simultaneously. Both bonds, either they increase or decrease in length simultaneously. Okay, at a time, no delay. See, both the bonds, they are going out and coming down, going upward and coming down at the same time, simultaneous. So bond length decreases or increases. Okay, now asymmetrical stretching, what happens? We can see here, one is decreasing, the other is increasing. In this, one bond length is increased and other is decreased. Okay, now the second type, bending vibrations. Bending vibrations. Vibrations or oscillations, these vibrations or oscillations not along the line of the bond. These are not along the line of the bond. Okay, they are also known as, they're also called as deformations. They're also called as deformations. In these vibrations, bond angle is altered. Bond angle is altered. It occurs at low frequency, 666 per centimeter to 1400 per centimeter. These are of two types: in-plane bending. In-plane bending, we have scissoring and rocking, and out-of-plane bending, we have wagging and twisting. Scissoring, rocking in in-plane bending, and in out-of-plane bending, we have wagging and twisting. Wagging and twisting. So in-plane bending. In plane bending, the first one, scissoring. This is an in-plane bending. We can see here, two atoms approach each other. Bond angles, they decrease. See, come together. Okay. This is an in-plane bending. two atoms approach each other. Two atoms, they are approaching each other. They are not decreasing or increasing. They are approaching each other. In this case, the bond angle decreases and increases. This bond angle, it increases or decreases. Okay. The second one, rocking. In this, we can see here, rocking. It's like rocking. Movement of atoms take place in the same direction, either left side or right side. They are okay, either left side or right side, the same. Okay, rocking, movement of atoms take place in the same direction, either here or here, same direction. Like we can see here, either that side or this side. Okay, these bonds, they remain a bond length. There is no change in the bond length. Okay, now bond I mean bond angle, there is no change in bond angle. Okay, same, just rocking. Okay, in the same direction. Now this, the second category, second type, outplane, out of plane bending or outplane bending. Okay, in this we have wagging and twisting. See, in wagging, what happens? Two atoms move to one side of the plane. Move to one side of the plane. They move up and down the plane. They move up and down the plane. One side of the plane. One side of the plane. Okay. See, suppose this is this. Suppose this is water molecule, and this is the plane. Okay. So they move up. They they move up and they move down. Okay. Suppose this is a plane. So atoms move up or down out of this plane. Okay. See, two atoms move to one side of the plane. Two atoms, they move one side of the plane. They move up and down the plane. One side of the plane. First, both the atoms, they move down and then up and down. Okay. Two atoms move to one side of the plane. They move up and down the plane. In wagging. In wagging. Okay. In twisting, what happens? One atom moves above the plane and the other atom moves below the plane. One atom moves above the plane and the other atom moves below the plane. Above the plane, below the plane, like this. So it is like twisting. Okay, we can see here in methane, only stretching we'll see. See here, upward, symmetric stretching. Symmetric stretching, and this is asymmetric stretching. These three are going out, and this one is compressing. These three stretching, these three compressing. So this is asymmetric stretch. This is symmetric stretch. Okay. Now this is very important. Number of vibrational modes. Number of vibrational modes. Number of vibrational modes. For we are only concerned with non-linear and linear molecules. Okay. So for there is a formula for non-linear molecules. For non-linear molecules, number of types of vibrations will be 3n minus 6. And for linear molecules, number of types of vibrations will be 3n minus 5. This is for linear molecules and this is for non-linear molecules. We have examples for HCl. HCl, This is a linear molecule, HCl. Okay, so this 3 into 2, number of atoms are 2, 1 and 1 and 2. Okay, so 3 into 2, 6 minus 5, linear molecule. Okay, so we get 1, so only one vibration. But in carbon dioxide, number of atoms are 1 and 2, 3, total 3. So 3 into 3, 9 minus 5. It is a linear molecule. It is a linear molecule. Carbon, oxygen, oxygen. So it is a linear molecule. Okay. And for linear molecules, the formula is 3n minus 5. So we have calculated number of vibrations will be 4. See this stretching, symmetric stretching, asymmetric stretching, and bendings. Okay. This you have to remember as far as exam is concerned. It may be asked. Similarly, here also one more example. Okay, IR active vibrations. Okay, we calculated there are 4 vibrations in carbon dioxide, 4 fundamental vibrations in carbon dioxide. So out of these 4 vibrations, how many are IR active vibrations? How many are IR active vibrations? So in order for molecules to absorb IR radiation, we know that vibration at same frequency as in light, but also must have a change in its net dipole moment. There must be a change in its net dipole moment. Then only it will be IR active. So we can see here there are 4 fundamental vibrations observed in carbon dioxide. This symmetric stretch. This net dipole moment mu is equal to 0. So it will be IR inactive. But in asymmetric stretching, there is change in dipole moment. So it will be IR active. Similarly, in bending vibrations also, there is change in dipole moment. So these two also will be IR active. So there must be a change in net dipole moment. Then only the vibration will, then only it will be IR active. Otherwise, it will not be IR active. It will not absorb this. This will not absorb IR radiation. This will not absorb IR radiation, and this will not seen in the spectrum. Suppose this is our spectrum, it will not be seen in the spectrum. Okay. Okay. Now we come to the applications of IR spectroscopy. Applications of IR spectroscopy. Applications of IR spectroscopy. Applications of IR spectroscopy. Where it is being used. Identification of substances. First, identification of any unknown substance, any compound, any given compound. The spectrums can be compared with the known one and with the unknown. No, because no two samples will have identical IR spectrum. We know that no two samples they have identical IR spectrum. So what is the criteria? Sample and reference must be tested in identical conditions, like physical state, temperature, and solvent must be the same. Anyway, so we know this fingerprint presence 600 to 100 per centimeter. Small differences in the structure and constitution of molecule result in significant changes in the peaks in this region. Hence, this region helps to identify an unknown compound. So this is the description, but you have to write only this. This can be IR spectroscopy can be used for identification of unknown substances. This description you should know. It is application. Other, we can study the progress of any reaction. Studying the progress of reactions. The other application. Observing rate of disappearance of characteristic absorption band in reactants. By this, a rate of increasing absorption bands in products of a particular product. For example, suppose the reactant, in the reactant we have this group, okay, which absorbs at this region, but in the product, if this is observed, we can conclude that there is a carbonyl compound or carbonyl group present in the product. Okay. So the measure the it this is first. The second one, we can study the progress of any reaction. The second one, okay. This is the third one. It can be used to measure the degree of polymerization in chemical compounds. It can be used to measure the degree of polymerization in chemical compounds, mostly in polymers. Okay. The fourth one, it can be used for the determination of molecular structure. It can be used for determination of molecular structure, used along other spectroscopic techniques. Identification is done based on position of absorption bands in the spectrum. For example, carbonyl group, it absorbs around the 17% So absence of band of a particular group indicates absence of that group in the compound. It means this carbonyl group is not present in the compound. Now, the next one, the fifth one, detection of impurities in the compound or the substances. So it determined by comparing sample spectrum with the spectrum of pure reference compound. For example, ketone impurity in alkanes can be done. It can be used. Okay. One is enough. Detection of impurities. Detection of it can be used for detection of impurities in compounds. The sixth one, this IR spectrum or IR spectroscopy is used for monitoring the structural plasticity of plant cell walls. This much is enough. It is used for monitoring the structural plasticity of plant cell walls. Okay. The sixth one. Protein quantification. IR spectroscopy is used for protein quantification. It is used for protein quantification. So, IR spectroscopy is one of the most well established techniques for the analysis of protein structure. It is used for analysis of protein structure analysis and elucidation of protein structure. Okay. This is enough, this much. Now, non-invasive blood glucose monitoring. This IR spectroscopy is used for non-invasive blood glucose monitoring. Non-invasive. Needle is not required. Non-invasive blood glucose monitoring. Near infrared spectroscopy is used across the earlobe to measure glucose. Amount of near infrared light passing through the earlobe depends on the amount of blood glucose in that region. Okay. So using this method, we can monitor the blood glucose level. Okay. Some other applications of IR spectroscopy. It is used for determination of unknown contaminants in industry impurity identification using FTI. FT stands for Fourier transform in mathematical term. We will study in mathematics Fourier transform and Laplace transforms. These are mathematical terms. So here FT stands for Fourier transform. Okay. So advanced version of IR. So determination of unknown contaminants in industry using Fourier transform IR, infrared spectroscopy. Determination of cell walls of mutant and wild type plant varieties using FTIR. Biomedical studies of human hair to identify disease states. We can identify disease states. Okay. It can be used for identify odor and taste components of food in food industry. It can be used for to identify odor and taste components of food in food industry. Now, the other thing, it can be used to determine atmospheric pollutants from atmosphere itself. It can be used to identify atmospheric pollutants. It is used for examination of old paintings. Used for examination of old paintings. Last but not the least, okay, it is also used in forensic analysis in both criminal and civil cases. In both criminal and civil cases. Example, in identifying polymer degradation, in determining the blood alcohol content, etc. So many things it can be used in forensic analysis. So this is very helpful to crack cases, civil or criminal cases. Okay. So this is all about IR spectroscopy. Hope you have understood.